Good afternoon, everyone. My name is Christos Karras. Today I will present you the paper entitled Maximum Likelihood Estimators on MCMC Sampling Algorithms for Decision Making. This is a joint work with my brother and colleague Aristeidis Karras and the professors Markos Avlonitis, Ioanna, Giannoukou and Spyros Sioutas. Starting off with the generalized linear mixed models, also known as GLMMs, which we utilize in the context of the paper. These are variations of generalized linear models, but the difference is that these include unobservable factors as extra components for variability. So typically, unobserved effects are handled by including random effects in the predictor of the generalized linear model. So the marginal likelihood function of the GLM is then derived by integrating the likelihood of another GLM with regard to the mixing distribution, which is the anticipated distribution of the random effects. We will see more details about that in the next slides. So moving on to the problem definition, in this paper we examine a clustering issue. So assume that we have n items, each of which has a binary answer of type shown in equation 1, where n signifies all observed variables and t denotes the observation time, so the time we observe a variable. Typically the time of the observation varies across elements, as some elements might be observed early while others might be observed late. So as a consequence, time points may also vary. So for the purpose of this paper, we assume that all elements are exactly equivalent in length and time points. And moreover, we suppose that all these topics fall into separate clusters. So the dependent expectation of a variable for each cluster is shown in equation 2, where for this equation, the cluster membership is denoted by U, and fixed and random effects are denoted by XC, IJ and ZC, where the C value is 1 or 2 respectively. So it's 1 for the top part of the equation, while 2 for the bottom part. So the function of connection is specified as in equation 3. So have f minus 1x, which is exponential x divided by 1 plus the exponential x. So due to the fact that the cluster membership U is often unknown in a traditional clustering scenario, we treat that as an effect of randomness. In the previous equation that we saw, we set the values 1 for P1, while U is set to 2 for the second part of the equation. So for randomness, we assume that it follows this distribution where PU is equals 1. So moving on to what we need to assess is this parameter omega, which is comprised by those hyperparameters veta 1, veta 2, sigma 1, sigma 2 and P1. So we need to assess that. So by using random effects, as some data might be missing, the function of likelihood for the whole set of data can be expressed as this big equation in 5. So where the normal distribution of FC equals this part, and FC basically signifies the density of it. So the dummy variable WIC, which is here, is associated with the cluster membership UI, and we have those two cases where WIC equals 1 if the element we look on belongs to the cluster C, or it equals 0 if the element doesn't belong to the cluster C. So incorporating the generalized linear mixed models, given the simulation parameters, which are n, the number of samples, t, the time we will run the experiment, and the hyperparameters, we can obtain the observed variables as y, as this matrix here, and we can also denote the unobserved or unobservable variables as y and z, as two matrices shown here. In order to compute the log likelihood, after giving the necessary parameters for each element or hyperparameter of omega, the enhanced log likelihood can be expressed as this part shown in equation 7. In order to perform the simulation step and therefore the maximization step of the Monte Carlo method, we have to calculate the augmented log likelihood, or at least to approximate it. So by taking expectation of the elements u, z and y, given y, under the current estimate of the parameters omega, utilizing an estimator m, the expected augmented log likelihood is defined as this big equation 8, which notice that the expected log likelihood of the omega m estimator can be decomposed into a separate component, which is done here. So we break down the elements and then we try to express that in a separate component. To calculate the maximum likelihood estimators for those partial derivatives, we have to approximate these parameters, which are given by equations 10, 11, and 12. So basically, we set those partial derivatives to 0 in order to get the maximum likelihood estimators, which is shown in equation 13 as p hat. To compute the maximum likelihood estimator of the parameter beta c, we use the famous direct numerical maximization method by Newton-Raphson. And the second order partial derivative of beta c is shown in equation 14. And this was all for the simulation step. Now we move on to the maximization step. So unfortunately, we don't know this distribution, which is contained by these parameters. So what we do, we use or utilize the estimators created in the previous step, in the simulation step. So we place the estimator here of omega m. So we use that in the m+1 step to approximate the distribution in order to generate equation 16, which is what we require to estimate. Here we have a flowchart of the proposed method, which is a simpler representation, but it's basically the summary of the paper. So starting off, we generate the fixed effects as we saw in the introduction. We generate z and y based on real parameters, and then we calculate the maximum likelihood based on those real parameters. We set the maximization step here as 0 as we reach the simulation step, and then we generate z and y based on estimated parameters this time. So we obtain the current log likelihood at this part, and then we move to the maximization step. We update the log likelihood by the maximum likelihood estimator at this point, and then we'll look for convergence if the values we have are close to the initial values or the true values. If these are close enough or are identical, we print out the results. While if there is a big deviation from the initial values, the process is repeated. So this acts as a genetic algorithm, sort of. So for the experimental results, we set the values for y to 0, 1 for the other parameters, and we perform 100 experiments. So we start the experiments by setting the initial values of the parameter omega. Remember, this is what we need to assess, which contains the hyperparameters. So for the first experiment, we set omega where beta 1 is 1.3, beta 2 is similar 1.3, sigma 1 is 2, sigma 2 is 10, and p1 is 0.6. We take these values arbitrary after several experiments, as these values are those that make the model operate smoothly. We did many experiments to pick the best values. So we conduct 1000 tests with various random seeds, and we mark down the result of the first 100 experiments, as well as the mean squared error of the 1000 experiments. Here are the results. We have a graphic representation. On the top two figures we have the convergence of beta and sigma. On the left hand side we have the convergence of beta. With blue it's highlighted the actual value and how it increases based on the estimator, and with orange we have the converged value. As you can see, they follow the same type of increase. On the right hand side we have the convergence of sigma. It also follows the same type of convergence. On the bottom two figures we have the convergence of the parameter p, and we have the mean square error. As you can see here on the left hand side graph, where we have the convergence of p, there is a slight deviation from the actual value, but this is due to the number of steps. Here we have plotted 50 iterations, while when we increase iterations, this deviation from the actual value is reduced. Here we have the tables containing the results. So we have the variables beta 1, beta 2, sigma 1, sigma 2 and p1. So we have the true value, which is set by us arbitrary, as we said before, and our program starts given an initial value which is different to the true value. As you can see, the converged value is close to the actual value. So basically our system starts from 0 and it performs sampling until it reaches the true value. So for all 5 variables you can see that the converged value is close to the true value. Here is 1.29 compared to the true value, which is 1.3. Here is slight above 1.30. Here is 198 compared to 2. For sigma 2 we have 9.1 compared to the true value, which is 10, and here we have 0.48 compared to 0.6. So these are all close to the true value, and on the bottom table we have the simulations for these parameters. We have the number of experiments. We perform for 1000 experiments up to 100, sorry, up to 1000, and here we have all the values and how the program operates, and the model tries to meet the converged value. So for the evaluation of the proposed method we use the mean squared error metric, which is defined as in equation 17, where we have theta, which is the true maximum likelihood estimator of theta in the nth experiment, and theta hat is the estimator of theta n. So the MSC score for all the parameters is shown in the figure we saw previously. It's shown here, which is kind of low for all the parameters. It's close to 0.05 for all the parameters except for p, which is 0.5. So generally the MSC should be within the value range of 0.2, whereabouts 0 value indicates that the model is almost perfect, and the value of 2 indicates that the performance is marginally acceptable. In conclusion, in the context of this paper, the basic functions of the MCMC methods were shown, as well as the inner workings of this method, along with Gibbs sampling and the proposed method for the Monte Carlo simulation maximization. So the results show that the proposed method performed smoothly using the estimators we created previously, And in respect to time, the system was capable to sample elements in a quite speedy way. Approximately took 1 minute to complete all 1000 experiments, and the MSc score for the 1000 experiments was also in relatively low levels, approximately 0.5 for p, while for the other parameters all of them were simulated efficiently and effectively. And future directions of this work include the integration of the proposed system with a Bayesian neural network in order to better highlight the findings in a more accurate and speedy way, and to approximate the underlying evolving distributions in a more steady way. Another future scope of this work is to increase the sampling rates and to reduce the MSE as low as possible compared to the method presented in this paper. And one last but significant improvement could be the reduction of the difference among the real and estimated coefficients. So we basically want to create a system that the converged values will be almost identical to the initial values. So that was all. Thanks for your attention. If you have any questions, please let me know. Thank you.